Hello, everybody. This is Miss Peachy from your WCA physics class, and I am doing a video recording to help you understand a little bit more with accuracy, precision, uncertainty, and significant figures. That's what this lesson is about. Our keywords are accuracy, which is how close a measurement is known to the accepted value. Percent uncertainty, the ratio of the uncertainty to the measured value written as a percentage. Precision, how close two or more measurements are to one another when they are repeated under the same circumstances. Significant digits, each of the digits in a number that are significant figures. Significant figures, numbers in a measurement that show how accurate the tools can be. And uncertainty, how far an experimental value may differ from the true value. So there's a lot kind of going on in this lesson, a little bit, lot to unpack. And I'm hoping to simplify it a little bit to make it a little easier to understand. Um, so the first part of the lesson talks a little bit about the difference between accuracy and precision. Accuracy being how close your measurement is to the true value, and precise refers to how close each measurement is to each other. So if I keep taking measurements and I'm getting very, very close to each other, that's considered very precise. Interestingly, you do not have to be accurate to be precise. You could be precise but be completely inaccurate. One of the good examples with this is with a dartboard, right? When darts are, for example, this is a person who's very precise. They're aiming at the bullseye, so they're not very accurate at all, right? The goal is to hit the bullseye, which is pretty big in this dartboard, let's not lie. But they're not hitting it. So this is where they're trying to get, this is where they're getting, and all of their measurements or all of their shots are very close together. So this has high precision but low accuracy. This has both high precision and high accuracy, right? You're right where you should be, and you are also repeatedly getting there. Here, you're really close. This is like me when I'm playing darts. I'm very, very close to the bullseye, but they're all kind of spread out. So some are really close to the 20, some are really close on this side, but they're all pretty close to where I want them to be. So this would be considered fairly accurate, but not very precise. So that's kind of giving you a visual example of what accuracy and precision are. So I think that concept's pretty easy to understand. Where you get a little bit more tricky is when we start talking about uncertainty, because there's a degree of uncertainty in every measurement that you make. Um, Depending on the instrument you're using, that uncertainty is more or less. Some instruments have smaller markings on them. So the smaller the marking on the instrument, and I mean like the more like smaller unit that's on the instrument, the more precise and more less uncertainty the instrument has. So just as an example of that, let's see, I just need to add a shape here, a rectangle. I'm going to put a rectangle here measuring, representing, nope, that's a text box, right? No, it's not a text box. Okay, representing a ruler. So let's say I have 1 inch markings on the ruler. One, or let's do centimeters. Let's be scientific. 2, right? If I'm trying to measure something and all it has is 1 inch measurements or 1 centimeter measurements, my bad. And I'm trying to measure this, right, this squiggle. I can say that I know the squiggle is between 1 and 2 centimeters. It's closer to 2 centimeters. It's obviously greater than 1.5 centimeters, but I can't be much more precise than that because I don't really know. So it's got some uncertainty, right? If I start adding like millimeter marks, so this is 1.5, 1, 2, 3. Oh, I did that wrong. 1, 2. Oh, that's right, Miss Peach. 1, 2, 3, 4. Here we go. 1, 2, 3, 4. Now I can be more precise. So I can say I can draw a straight line maybe. We're just putting a caveat there. Okay. down from the end of this all the way down. Oops, try that again. Try that again. There, all the way down, and I can say, hey, this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. It's greater than 1.6, almost 1.7 centimeters. Do you see how that measurement is a much more accurate? It has less uncertainty to it. I'm still not exactly sure how much it is. Is it exactly 1.7? Is it 1.69? Is it 1.68? Is it 1.71? I don't know for sure, but I have a greater degree of I have a greater degree of certainty than I did previously. So that's kind of what we mean by that, okay? I haven't used this whiteboard for a while, you guys, so bear with me while I try to figure out how to erase everything. Just select it all. I'll just throw it away, scoot it out of the way. All right, so the example they're giving you in the text has to do with weight on a bathroom scale. And the first thing that I think is a little bit confusing here is they don't really define what uncertainty is. So I want you to remember this, that uncertainty is 1/2 of the range. That's true for all of these, right? It's half the range. Well, we said here on this example, it says you step on a bathroom scale and the range is between, you're kind of close to 142. Like anything beyond 142 is an estimate. So we're using 142 as kind of our base. You weigh more than 141.5, you weigh less than 142.5, but somewhere in between. And so the range here between markings is 1 pound between 141 and 142. Uncertainty is half the range, so half of 1 is 0.5. So our uncertainty in this example is 0.5 pounds, right? That's the uncertainty in this example. And so we're taking we're close to the 142 mark. So that's our first, we say we're 142 plus or minus the uncertainty, which is 0.5 pounds. Okay, so this represents what we're not clear about. We don't know if it's less than 142, 142.5, or if it's more than 142, 140, or 141.5 or 142.5. We know it's somewhere in between. Why is there uncertainty? Well, we talked about the fact that some instruments are not as precise as others. Sometimes we have less markings on there, therefore it has more imprecision. Sometimes your eyes aren't super great. Maybe you forgot your glasses that day. You're not doing a great job making your measurements, or you're being sloppy with the measurements. The thing that you're measuring is not perfectly linear, so it's difficult to kind of get an accurate, precise measurement. There's a lot of things that might influence that, right? So that's what we have to look at here. I found the eraser, you guys. Awesome. Okay, exciting. So moving on ahead, now we're talking about let's take that percentage, that plus or minus 0.5 pounds. Let's take that accurate, or that uncertainty, excuse me, and let's make it into a percentage. So you use this percent uncertainty formula here to make it into a percentage. So what we're going to calculate is, in the previous problem, we had that 142 plus or minus 0.5, right? Pounds. Let's not forget our units, you guys. Units are important. So here we're saying, okay, this is that plus or minus. That's your uncertainty in units. This is that kind of average measurement or measurement there. So we take that 0.5, you divide it by your 142, we take the whole dealio and multiply by 100. And it shouldn't say 100%. That's incorrect. You're multiplying just by 100. And that will equal the percent uncertainty. So yeah, don't hit your percent key here, okay? That would make it a wrong measurement. So when I do that, you guys, I use my handy dandy TI-30 calculator. I take 0.5 divided by 142 and multiply by 100, and I end up with big long number, 0.35, and whoopsie doopsies, we don't have that actually on here. But 0.35 to 112676. But that's too many numbers, so we'll talk about significant digits in a minute. Let's just do another example here, okay? Because they actually don't go through that one. Clear screen, here we go. So they talk about shrimp. We all love shrimp. Shrimp's good. Maybe you don't like shrimp. I didn't like shrimp until I was like 40. I thought it was gross, but actually it's pretty decent. So I still kind of get squeebed out by the ones with the feet and stuff, but that's neither here nor there. So you purchase 4 bags of shrimp, and they don't make them exactly the pounds that are listed. It's usually a range, right? So you have 4 different bags. The first bag weighed 1.8 pounds. The second bag weighed 2.2 pounds. The third bag weighed 1.7 pounds, and the fourth bag weighed 2.2 pounds. So remember that uncertainty is half of the range. So our range is between 2.7 and 1.3, or 2.3 and 1.7. Man, Miss Peachy, my name is not Miss Peachy anymore. It's Mrs. Wild, so I have to keep getting that right. But Mrs. Wild needs to have some more coffee, I think. But anyways, we take that 0.6 pounds, which is the range, and divide it by 2 to come up with your uncertainty. So your uncertainty is plus or minus 0.3. So now we have uncertainty. We can find the percent uncertainty because we have a measurement of 2 pounds plus or minus that 0.3 pounds. Now, often you'll put a 0 as just a placeholder there to make it so that the decimal is visible. So how did I get to 2 pounds? Well, we know that the bags came in 2 pounds, but that's not really the best way to do it. The best way here would be to take all 4 of these, add them together, and then divide by 4. So you're getting the average. So the average of all of your measurements is actually 2.0 pounds, okay? That's how we got that number. All right. So now we can find the percent uncertainty using that formula that we were given. So percent uncertainty is equal to this number here, which is your uncertainty in units, right? Divided by this number here, 2.0, times 100. They didn't put the percentage here, you notice, so that was a mistake before. So you don't want to do that mistake because it'll change the value. So that gives us, if you did your calculations correctly, 15%. Now what that means is that 2.0, we could write this as 2.0 plus or minus 15%. That's fine. We could also say, hey, what's the highest amount that it usually could be then? So we could backwards calculate a little bit and say, well, 15% of 2, what's 15% of 2? 2 times 0.15 equals 0.3. So it's generally between 2.3 is the highest value, right? And the lowest value would probably be 1.7. So you can actually get the range back. Isn't that cool? 2.3 to 1.7, just by knowing that percentile. Now that's how we got it to begin with, but sometimes they'll give you this and ask you to calculate the highest value or to calculate the lowest value. So that's how you would do that. You find the percent, 15% of 2.0 is 0.3, and then you just add or subtract the 0.3. Okay. So You then have certain uncertainty by multiplication or division. Let's see what I can do, you guys, here. Can I erase entire stroke? There we go. All right. So sometimes there are two things that you need to add together, or excuse me, multiply together or divide together, and you would have a degree of uncertainty in each. So when that happens, you just add the uncertainties together. So for example, I think a better example or the easier example is calculating area here. Area is length times width, right? Area is length times width, or base times height, whatever, it doesn't really matter. Is area. It says you have the height of a wall and the width of a wall, so we're going to do 3 times 4.50, and that gives you 13.5, and that's square meters. And then the different let's see here. The uncertainties it says are 3% and 2%. So the person, whoever did this problem, took this, they used this formula, or the formula that we did in the previous slide, right, to get the percent uncertainty, and then you just add those percents together. So it ends up with a 5% uncertainty. Okay. And again, that means 5% of 13.5. So let's do that. 13.5 times 5, or 0.05, is 0.7 if we're rounding. If I add 0.7, that gives me 14.2. If I subtract 0.7, that gives me 12.8. So that's my range, right? It might not be exactly 13.5. It's somewhere between 12.8 and 14.2. All right, now we're moving on to significant figures. And yes, we kind of combine them as well at some point. So the significant figures talks about like how many decimal points you report your answer to. And that is determined by the instrument you're using. So if you're using a more precise instrument, you have more significant figures. If you are using a less precise instrument, you have fewer significant figures. It represents the degree of uncertainty. So more uncertainty would be fewer significant figures, and more certainty, if you will, would be more significant figures. Specifically, it's going to talk about zeros. I'm going to talk a little bit about zeros, not using this page, but skipping ahead a little bit to this page, because I think they do a better job on this page of explaining the rules of significant figures and zeros. So leading zeros which occur for the purpose of showing place value are not considered significant. So in this example of 0.00976, these all are leading zeros, so they are not significant, and only the 976 are. So we have 3 significant digits in this particular example. If a 0 is popped in the middle of a number, then it is significant. So in this example of 1.053, 0 is significant because it falls between numbers. Trailing zeros are significant only if they occur at the right of the decimal point. 1.600 has 4 significant figures because those 2 zeros are to the right of the decimal. 1,600, the 2 zeros are to the left of the decimal, because you have to imagine, of course, that imaginary decimal. I lost my numbers right here. And a 0 by itself only has 1 significant figure. Going back to where we were a minute ago, this also explains that when you have zeros to the right of the decimal, like 6,700, sometimes it's kind of hard to tell if it's significant or not. We say it's not significant, so if you want to make it significant, you have to write it differently. So remember that significant digits represent how precise you were when making your measurements. Let's say I was measuring a tree and I report the measurement as 180 feet, right? It's kind of a big tree, but I want some zeros. So the question is, did I get up there and measure exactly 180 feet? Or is it like an estimate to the nearest tenth, right? If I write it like this, it's telling me I'm estimating to the nearest tenth. If I want to tell people, no, 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 I'm not estimating to the nearest tenth, I literally measured it in some miracle of nature. It is exactly 180 feet. I would write it like this instead. 1.80 times 10 to the 2 feet. That allows me to make that zero significant. So now this number here has 3 significant digits. If I'm estimating to the nearest 10, I write it like this. Right? Still the same, still comes up to be 180 when you figure it out without the scientific notation, but scientific notation shows us the number of significant digits. So the only reason you would put a 0 here is if you actually physically measured it, if it's considered significant. All right, so when we are using significant figures, there are rules. There are multiplication and division rules and addition and subtraction rules. So significant digits are each of the digits in a number that are not only serving as placeholders, indicating the accuracy and repeatability of that measurement. Thus, the final answer cannot be greater than the number of significant digits in the least precise value. So when you are reporting your answers, your answer cannot have more significant digits than any one of the measurements you made. So let's say we're calculating the area of a circle. So you're using pi, which has a lot of significant digits, and you're using a measurement of the radius of the circle of 1.2 meters. Because 1.2 meters is the least significant, it's 2 significant digits, you have to report your answer in 2 significant digits, okay? You cannot report 4.52 or 4.524, right? You have to measure or report your answer to the least number of significant digits. During addition and subtraction operations, the answer may contain units only up to the last digit for the least amount of precision. So we have a bunch of objects, we're putting them on the scale, 5.02, 16.7, 3.012, and we add them all together. The least amount of significant digits here is 3. So let's see here. So the lowest precision is using the tenths place here, right? So 16.7 is a measurement to the tenths place. So we also report our answer to the tenths place, okay? So we look at the measurement with the lowest precision, which is the number of decimal places. So it's a little bit different. This still has 3 significant digits each, but let's say this answer had been, 5.7, that still would have been the right way to report it because we have to use the lowest precise answer to the tenths in this case. So it's slightly different than the multiplication and division rules because you're not using the number of significant digits per se. It's the precision of the measurement to the tenths place, to the hundredths place, to the ones place, that kind of thing. I think that is everything. Let me just make sure I'm double checking here. Okay, we don't need that one. We don't need that one. Yeah, I think that's pretty much everything in this lesson. So if you have any questions, let me know. I'm more than happy to work with you. Have a wonderful rest of your day, everybody, and we'll talk later.